We continue with the series. Now we are going to see what happens when we add two series. There are some interesting situations. So this is essentially the property that is important. There are two of them. So if I have two converging series, so series AK is convergent to a number A, and series BK is convergent to a number B. So if I add AK and BK, what will happen is I actually add the two series, and since each one of them is convergent, the sum is also convergent, and it's converging to A plus B. That's what we would expect anyways. And also if we subtract two series that are convergent, both of them, then the result is also a convergent series, and the sum is A minus B. Also, if we have a convergent series and we multiply the general term by a constant, obviously we can take constant out. So since the series is convergent and its sum is A, then the sum of CAN of that series is CA. Obviously that's what we expect. That's true for any constant. So those are the properties that we normally would expect from two convergent series. Now, another important property is when one series is convergent and the other one is divergent. In that case, the sum of the general terms produces a series that is divergent. If we subtract them also, we get a divergent series. So you see, one of them must be convergent and the other one divergent. In that case, if we add them, the resulting series is divergent. If we subtract them, the resulting series is divergent. And if we multiply by any number a divergent series, well, we get another divergent series, obviously. The number needs to be different from 0, because if I multiply every term by 0, I'll have just 0 plus 0 plus 0 plus 0. That would be convergent. So that's why we have here condition. The constant by which we are multiplying needs to be different from 0. And finally, if I have a convergent series, I multiply it by any number, the result will be a convergent series. So for now, what we learned is adding two convergent series, we get a convergent series, or subtracting them, or multiplying a convergent series by a number. If I have one convergent series and one divergent, a sum is divergent, difference is divergent, multiplying a divergent series by any number different from 0 is also producing a divergent series. So those are important things. We will see some examples. It is important to pay attention to the situation where we have two divergent series. In that case, situation is complicated and we need to examine it case by case. So one example here, we have a series where the general term is 2. So 2 plus 2 plus 2 plus 2 plus 2 plus 2. So since general term is 2, the limit of the term is 2. It's not 0. Therefore, we know that the series is divergent by divergence test. Also, series of 5. So we had 5 plus 5 plus 5. Since the general term is 5 and its limit is 5, so it's not 0. That means by divergence test, the series is divergent. So if I add those two arguments, 2 and 5, I'll get a series that is series of 7 plus 7 plus 7 plus 7. Obviously that one will be also divergent because the general term is 7, limit is 7, and it's not 0. So by divergence test, this will be a divergent series. That's what we would expect anyways, naturally. However, a simple example, here I have again my series of 2 plus 2 plus 2, so that one is divergent. And then I take the series minus 2, so minus 2 plus minus 2 plus minus 2 plus minus 2. So the general term is minus 2. The limit of the general term is negative 2, which is different from 0. So by divergence test, this series is divergent. However, if I add the arguments, the general terms a and b, I have 2 plus minus 2, so 2 minus 2 is 0, and I add 0 plus 0 plus 0 plus 0, that would be a convergent series. So be careful when you have two divergent series. We really need to examine the situation carefully. Our result is for two convergent series, we add them or subtract, we get convergent series. If we have one convergent series, one divergent, if we add them or subtract, we get a divergent series. However, if we have two divergent series, in general, we need to be very careful. We cannot conclude anything. We need to check case by case. Here are some quick examples, simple ones. So if we want to see if this complex series here is convergent or divergent. So I have 1 over k plus 1 over k squared. So the series 1 over k, we saw it is harmonic series. It's also a p series with p equal 1, and we know in that case the series is divergent. On the other hand, series 1 over k squared, that's a p series with p equal 2, and that's a convergent series. So we have one series that is divergent and the other one that is convergent. If we add their arguments, we get a divergent series by our theorem. Another example here, we have a series composed of two pieces. We can recognize the first piece and the second piece. So the expression 3 over k to power 5. So this series here we can factor 3 obviously. And then we get 1 over k to power 5, our series. So this is a p series with p equal 5. And we know that this p series is convergent. We don't need to show anything, we just state it properly. So a number times a convergent series is a convergent series. So no issue. Also, this expression 4 over 2k, so 4 can be factored and we have 1 over 2 to power k. We already saw that this is a geometric series. If we write it out a little bit, we recognize that a is 1 over 2 and then the ratio is also 1 over 2, which is smaller than 1 in absolute value. So that means that our geometric series is convergent. If I multiply a convergent series by a number, I get a convergent series. So I have two convergent series. If I add their general terms, I get a new series that is convergent itself. That's what the theorem told us. Another example, similar, again 1 over 2k, 2 to power k is convergent geometric series with general term 1 over 2 and ratio 1 over 2. We can even compute the value by the formula. So the sum of the series is there. And we have also another part that is telescoping series. We already saw this. Using partial fractions, we can factor the argument in two pieces and then write the partial sums. And the limit of the partial sum is the sum of the series. So that way we have the series equal 1. So we have two converging series. Now we put everything together. The first series had a 3 in front, so we don't forget that part. So 3 times 1, which is the sum of the series, plus sum of the series here is 1 also. So at the end, the sum of this combined series is 4. And since it is a sum of two converging series, this series is also convergent. Obviously, since each of these series, in each case we are able to find the sum, so we are able to add. In some cases, the sum is not known, so we cannot really compute, but we can still say if the series is convergent or divergent. Another case, here we have this composed general term, so one piece and the other piece. So if we start with the easier one, the series k over k plus 1, we note that the general term of this series converges to 1, so it doesn't go to 0. And we know by divergence test that this series diverges. So that's all we need to say. So we have one divergent series. Let's see what happens with the other series. We have here 7 to power n plus 1 divided by 10 to power n. So the powers are not exactly the same. We will make sure to rewrite the general term so that the power is upstairs and downstairs is the same. So 7n plus 1 is 7 times 7 to power n, obviously. So now we have this general term, and we can write this geometric series. We see A here, and then we have R. And R is 7 over 10, which is smaller than 1. So we have our geometric series with R 7 over 10, which is smaller than 1, and that geometric series is convergent. Therefore, we have one series that is divergent, because its general term is not going to 0, so the limit is 1 of the general term. And the other series was convergent geometric series. So we have sum of two pieces, one convergent, one divergent, and the resulting series, as per theorem, is divergent. Another example, here we have one piece that is geometric series, and the other one will be telescoping series. We already solved this problem, and we found that the telescoping series has the sum equal to 1, and then the geometric series, if we write out a couple of terms, we see that the first term A is 1 over E, and the common ratio is 1 over E also. 1 over E is smaller than 1, so this is a convergent geometric series. Now we have a formula to compute the sum of this geometric series. We use it. So we have sum of the telescoping series equal 1, and sum of the geometric series, here 1 over E minus 1. That means that the sum of this composed series is sum of one series plus sum of the other, because both of them are convergent. So we add them simply, and we get another convergent series. And in this case, we are able also to find the sum, because we are able to find the sum for each piece, and then we can just add the sum of each series to get the sum of this new combined series. So this is quite straightforward. Another example, this time with two convergent geometric series. So if we write out our first term will be negative 0.2, and then we will find out that our ratio is also negative 0.2. Now absolute value of this is 0.2, which is smaller than 1, so we have a convergent geometric series with 0.6. Here, pay attention, we start from 1, and the exponent is n minus 1, so the first term is 1 minus 1 here in the exponent, so 0. 0.6 to power 0 is 1, so the first term will be 1, and then the common ratio is 0.6. So again, we have common ratio smaller than 1 in absolute value, so we have convergent geometric series, and we are able to find its sum here and here, both cases. Therefore, I have two convergent series. If I add them, I get another convergent series, and the sum of this new convergent series is simply addition of sums of each of the components. So we use the formula for the first and for the second. So A divided by 1 minus R, and here also A, which is 1, divided by 1 minus R. We shake this a little bit, and we find the value of the sum of this new composed series. Finally, another example. Here things look a little bit complicated, but we can split this in two pieces. The general term, we see that we have 2 over E to power n and 4 over E to power n. Now 2 over e to power n, if we write out a little bit, we will write a couple of terms and we will realize that we have geometric series. The first term is 2 over e, and then the ratio turns out to be also 2 over e. Now e is 2.7 something, so 2 over e is smaller than 1. So we have a convergent geometric series in this case. Now 4 over e, in this the other case, a is 4 over e, and turns out that the ratio is also 4 over e. Again, e is 2.7, 4 over 2.7 is bigger than 1. So we have a geometric series with common ratio bigger than 1, which means that this geometric series is divergent. Since it is divergent, we have the case where one series is convergent and the other one is divergent. Therefore, the combined series here diverges by our theorem. So these are just some simple applications of the theorem and the result that are useful.